Thank you very much for being here today so early in the morning and so lately in the week. So I'm an associate professor from ENSTA Bretagne, and I do my research in lapstick. And yes, my job today is to speak about Bayesian inference and variational approximation that I use in my early day life, and I will try to convince you that they are good tools for you too. Okay. So I divide my presentation into three parts. The first one, the much boring part, maybe, will be to introduce and to recall some theoretical basics on Bayesian inference and variational approximations. I will be my best to be the most interesting for you. And then I will go to two different applications of the use of variational approximations. I worked on optics when I was a postdoc in Paris with a collaboration with Sylvain Gigant, and more recently some works in underwater acoustics in DOA, so direction of arrival estimations, in spatially fluctuating oceans. Okay, so let's begin with the boring part. So, when you say that you want to do Bayesian inference, what you say is that you will use some observation of something, the object of interest you are interested in, and to make an inference about the probabilistic distribution at the origin of the object you are interested in. And how do you do that? You have to give you a model, a probabilistic model of what you are interested in. And this is actually at the heart of the Bayesian framework. I mean that the Bayesian framework makes explicit some assumptions, some knowledge you have on what you are interested in. And this is where you can put some physics. And, but there are still models, namely all models are wrong, I know that, but some of them are useful. And don't forget that at the end you just have an interpretation, you don't have the truth. You can't have the truth, so you have an interpretation of your problem, your phenomenon, rather than an explanation. At the beginning of the Bayesian framework, you have a guy, this guy here. This guy here, whose name is Thomas Bayes, and he wrote this famous formula here. I will use it in the following of the presentation. He presented his work to the Royal Society and died the year after, I think. And 10 years after, this result was rediscovered by Pierre-Simon de Laplace. He didn't know anything about the work of Thomas Bayes. It was nothing personal, but okay. And okay, so as you see, this is a very old domain. And it encountered some difficulties to emerge, actually, and to be used in practice because of computational reasons, actually, because it was difficult to deal with this kind of framework in practice. I will then speak a little bit more about that, but actually this is the success of the variational approximation, because in comparison with some Monte Carlo methods, you have maybe heard of them, this is very, well, not very simple, but okay, quite simpler. Okay, to make the things more concrete, let's do that you have an object which is emitting something. It could be light or sounds, and these emissions will be propagating into a medium, something, and this medium combines in a certain way the information which was emitted from the object, and at the end you have some sensors here that receive a cry, the combination of all the information that were sent by the object. So the problem is, okay, if I have my observation on my sensors, how can I infer some information on my object? This is actually an invert problem, and when you want to deal with this problem into a Bayesian framework, you will need three ingredients. You will need an observation model, a prior model, and a Bayesian estimator. Okay, let's go to the observation model. So the observation model here is attached to those sensors, to the observation you have, and it will express the information you have on the way your data have been acquired. So it depends, it is conditional to the phenomenon you are interested in, so the object, and also the way your information has been propagated until your sensor, to your sensor, sorry. So in practice and more formally, we can propose this general formulation. So Y here are your observation, and you can say, okay, my observation is a function of the variables of interest, which combine, which merges actually the information, the information on the object and the medium, for example. And because the world is not perfect, you have always some noise. Always, not always, but okay. This is quite often, actually. And typically, if n is a Gaussian noise of variance sigma n, then you will have an observation model that links the observation conditionally to the variables of interest as a Gaussian, whose expectation will be f of u, and the variance sigma n, which is the variance of the noise. Okay, this is just to give you some example. Okay, if you are lazy, you can just stop here and just, okay, it was very difficult to have this observation model. I can't do less. I can't do anymore. Let's try to do something with that. And then what you can do is to compute a maximum likelihood estimator. In that case, you will try to maximize the likelihood function, which is nothing more actually than the conditional distribution of your observation given your variables of interest, but written in another way. Okay, just to make artificially the inversion that you want actually. Namely, try to get some information of the over the parameter given the observation. Okay, but this is just artificially. If you are not so lazy, you can try to give more insight, more information into your to your estimator. And if you want, if you can, also it's not always the case, you will then define a prior model. Namely, some information some knowledge you have on the object or the medium, and so just to give you the importance of the things is that in this prior model you have all the information available a priori, so the knowledge you have on the variables of interest. For example, if you have some information about the way the propagating medium here, you will put it in this prior model. Okay. Once you have your prior model, you can define 3 new important definitions. The first one is the joint distribution. Namely, you can say, okay, the probability density of y, so my observation and the variables of interest, is the conditional distribution of the observation given the variables of interest times my prior model, right? Once you have your joint distribution, you can then compute the marginal distribution, for example, over the observations. And here, you just the definition is that you will integrate over all possible realization of u, of the variables of interest, of your joint distribution. Once you have your marginal distribution, you can compute the posterior distribution, and here you can find the Bayes formula again, where here you have the marginal distribution over of the observations and something which is much more complicated at the end. Okay? I may be too fast, I'm sorry. Do not hesitate to interrupt me. So here are the Bayesian key points. So just stop a little bit here. to make some remarks. So here the prior model is very important. This is at the heart of the Bayesian framework. It gives you some quantitative description of the variables of interest. So everything you have on the uncertainties and the information you have on the variables of interest may be put in the prior model. Then it integrates naturally a priori information and the imprecision of the information into the inferential procedure. We will see that in the following. So this is for the prior model. Once you have your prior model, you can define then the posterior distribution, which is a fundamental concept in the Bayesian paradigm. Because here you have naturally the inversion you wanted to have with the likelihood function. You will have, if you go just a little bit before, you will have here the inversion which you tried to get with the likelihood function, and here this is naturally implemented by the use of the prior model. And yes, so it operates conditionally on the observation. So you have a probability of the variables of interest given the observation. Okay, third ingredient you need to have a Bayesian inference, the Bayes estimator here. So this estimator, this is your estimator. You have to say what is important for you in terms of error and in terms of yes, in terms of error. Actually, I would say that I will told you more a little bit here on this slide. So a Bayes estimator is defined according to a cost function here. So you can define different cost function. I will give you two examples here. And this is the general definition of a Bayes estimator. So you want to minimize the expectation, the posterior expectation of this particular cost function. So here, this is just the development of this equation here. And so what you see here is that the posterior distribution, which was really important, which is really important in the Bayesian framework, and to particularization of this particular general definition is the minimum mean square error. In that case, you need the L2 norm, and you get finally at the end this type of estimator, so MMSE. And for the maximum a posteriori estimator, which is famous also in Bayesian inference, you have this particular cost function, and you get finally at the end this expression. So here, for both of them, you can have some intuition about what you are doing. In that case, you say, okay, my estimator, I want it to be the expectations, the average, actually, over all possible realization for my variables of interest, according to the posterior distribution, so according to what I know about my observations. And for the maximum a posteriori, the idea here is just to say, okay, I want the maximum, I want the realization that give me the maximal probability that explain my observations. Okay? So in practice, this minimization here can be made difficult for at least two reasons that I wrote in blue here, actually. So an explicit computation of the posterior distribution may be impossible, so this posterior distribution here, and the analytical integration may also not be possible. So to circumvent these difficulties, you have two major families, two possible ways to deal with that. Monte Carlo methods and the Bayesian variational approximations. So Monte Carlo methods are maybe the most popular ones. You will approximate this integration by something which is finite, by a finite sum over a finite number of realizations. And these realizations, these samples, are generated according to, in a way that it tends toward realization of the target law, namely, according to this, we try to approach this posterior distribution. These methods are very are old, actually, are very old. And this is why, in my opinion, this is why Bayesian inference, Bayesian framework has not known the success that it should be. And actually, because these methods are very costly in terms of computational times, and they do not offer any explicit expression of the posterior distribution here. So it works, but it needs some computational resources that maybe you don't have. As an alternative, you can do some Bayesian variational approximations, where you will try to define an approximation directly, an explicit analytically expression of the posterior distribution here. So these are approximations. So here you can try to turn towards the exact law. In that case, no, or in some cases, yes. I will tell you that a little bit in the following slides. But it comes with less tedious computations, and it proposes an explicit expression of the posterior, of the target law, of the posterior distribution. So I find it very elegant in comparison to Monte Carlo methods. This is my opinion. Okay, so I will speak a little bit more about Bayesian variational approximation. Okay, you want to find an approximation of the posterior distribution. How do you do that? You have to define a distance between the target law, so the posterior distribution, and the approximation you want to build. And in that case, the most well-known, maybe, distance, which is not a distance, actually, is the Kullback-Leibler divergence. So this is written like that. So one way to build this approximation is to say, okay, I want to minimize the Kullback-Leibler divergence with my target here. And because it's sometimes difficult, okay, I could add some constraints over the distribution I want to build. Okay, so if Q here is equal to the set of probability densities, then you get naturally here Q will be equal to the posterior distribution. All right. But if you make some, it has no interest actually, because it's difficult to have that, to have hits to construct it. So maybe you can do some restriction over the set of your optimization. So there is different approximations according to the definition of Q. And I will present you two of them, the mean field approximation and the beta approximation. So let's go to the mean field approximation. Yes?
On the previous slide, do you construct this for each and every observation Y, or how does this enter in the minimization procedure? Do you want this Q to be a good approximation for a couple of Y, or how does this...
You mean the observation here? Yes. No, it's the entire set of observation. But actually, you can do whatever you want. If you want some a posterior distribution according to a specific observation you get, then you can build something which is specific to this particular set. And what is maybe I benefit from your question to say that here you take into account in this particular U. All variables of interest, and after that you can also make some difference between them because you have this set of constraints that actually you construct whatever you want. Right. I don't know if I well understood your question. Okay, so the mean field approximation assumes a posterior independence of the variables of interest. So in that case, if I have n variables of interest, I will say, okay, my posterior distribution, I want it to be factorized, to be factorized like that. Namely, each variables here, ui, is assumed to be independent from the other. The minimization of the Kullback-Leibler divergence under this mean field approximation can be addressed by a coordinate descent algorithm, which is quite interesting for us because it will ensure us that we will in fact try to minimize actually the Kullback-Leibler divergence. To get you some insights about this procedure, assume we want to optimize only one of the factors, say this one, I, so that you have, if I integrate the factorization into the minimization expression, the Kullback-Leibler divergence, you have this particular expression here, where I put I made a difference here to this particular factor I'm interested in. In that case, since I have integrated the constraint inside within the Kullback-Leibler divergence, I just have a constraint that expresses the fact that I want a probability density. Okay. So if I just consider this particular case, I just optimize for this particular factor, I get a closed form solution, which I wrote here, and where I see that, okay, this is proportional to an exponential, and here inside you have an integration over all the different factors, all other factors, different from I. Okay? Okay, so this is interesting. And okay, then the VBEM algorithm, so the variational bias EM expectation maximization, algorithm, relies on this particular expression. It says, okay, we can do an iterative procedure in which at each iteration we update all factors of the approximation by just focusing on one particular variable and keeping the others unchanged. And we do that at each iteration for all different factors. Okay, so by doing that, we ensure that we converge to a saddle point or maximum of the problem. And what is interesting also, because of this particular form, factorized form, is that after convergence, the posterior distribution in which we are interested in is simply given by this factor, so the corresponding factor in the approximation, in the mean field approximation. Okay? I love the mean field algorithm, the mean field approximation. So the mean field approximation is quite sympathetic, actually. It offers a nice framework and simple framework actually to implement an approximation of the posterior distribution, but it relies on a very strong constraint, namely the posterior independence of the variables. And in practice, this is rarely encountered. So we may search for another one which is closer to the true distribution, and this is the goal of the better approximation. So the better approximation, is much more complicated. I have to make some to put some new definition before I go further into the algorithm. But I will try to not losing you. Okay, so let's assume first that joint distribution here, so P of U and Y, so the variables of interest and your observation, admits a particular factorization, this one. So here I introduce a new notation here. U of epsilon is a kind of partition of the variables of interest, of the set of variables. Okay? I will give you a little example in the following slide. then if you have this particular formulation for your joint distribution, and so you can consider this constraint, this particular factorization, in which you can recognize a similar factorization as in the prior model, the joint distribution. And here you get something which is a little bit more complicated, in which you have this di here, which is the degree of the variable ui. This is the number of factors, f of epsilon, depending on of the variables ui. Okay, let's take it, just accept it, and then we will go further in the explanation. What is interesting here to say, okay, just to have the take-home message, is that the minimization of the Kullback-Leibler divergence under this particular set of constraints can be addressed by a belief propagation algorithm. To explain, to go further in the explanation of the belief propagation algorithm, I need to introduce a factor graph. A factor graph is a bipartite graph expressing the factorization structure of the joint probabilities that I showed you just in the slide before. So you get variable nodes here as circles and factor nodes here as squares. This is an example of a factor graph for this particular joint distribution. For example, here you see that the factor node here will be linked to 3 variable nodes, so U1, 2, and 3. And then this particular U3 will be linked to 3 different factor nodes. In fact, you find U3 in F5, F4, and F3. Okay, so this is just a way to see, to construct, to draw your joint distribution. So the belief propagation algorithm relies on this particular factor graph by defining 2 types of messages. So it's based on the transmission of these messages all along the factor graph, all along the edges of the factor graphs. So 2 types of messages. One type of message going from factor nodes to variable nodes, and one type of messages coming from one variable node to a factor node. What is interesting to see here is that here you have the prior information, so the joint distribution you put at the beginning of your in the modelization step of your problem, okay? And after that, you see that you have an interdependence between the messages, okay? So the belief propagation algorithm will initialize all messages to 1 at the beginning, and then it iterates the messages until convergence. And at convergence, you will get this definition for the marginal a posteriori of the variable ui. You say, okay, this is a product of all messages which are arriving at my variable nodes. So, for example, the posterior distribution of Q of 3, U3, will be the product of these messages coming from factor node F3, these messages coming from factor node F5, and this one coming from factor node F4. So this is a little bit much more complicated than the mean field approximation, but okay, it's okay. And what is maybe interesting for you to see is that if there are no loop in the factor graph, so this was the case in my example. Here, you have no loop, okay? A loop will be, for example, to join, to link F1 and F2 by a variable node, okay? So if you have no loop in the factor graph, you are ensured to converge in a finite number of messages. So you have only 2 messages per edge. And you get, and this is quite interesting for you, an exact estimation of the posterior distribution. You have well-known algorithm in case of Markov chain, the Kalman algorithm for continuous variables, or the Bézier algorithm for discrete variables are some particularization of the belief propagation algorithm. Okay? If there are loops in the factor graph, you can do the procedure. You can use the procedure of belief propagation. You have a sequential update of the messages until a potential fixed point is reached. And you know there is a theorem which is recalled in the paper. I will give you the reference at the beginning of the talk, this part. So fixed point of the belief propagation algorithm are stationary points of the minimization problem under the beta approximation constraint. Okay? But yes, this is something I didn't say. You are not ensured at all to converge, right? So if it converges, it can converge to a potential fixed point, and then you get the solution of your work. Okay, so this is my last slide for my boring part. If you want more information about Bayesian inference, I recommend this book, which is really a nice book from Robert. And then you have these 2 particular papers that are really nice to understand variational approximations. So beta approximation and belief propagation algorithm, for example, and the mean field approximation too. Okay. Is that all right? Okay, let's go to the application part. Okay, I recall everybody that I'm not a physicist, okay? So this is something I worked on with Sylvain Gigon when I was in postdoc in Paris. So you have a monochromatic laser here. Here you have a telescope which is going to get your laser here as an homogeneous beam. And this beam is then refracted to a DMD, a binary amplitude SLM here, in which you have 2 position only for the mirror, so 1 or 0, on or off. And this beam is then refracted, so focused through a lens here to a scattering medium, which is nothing more than a white paint layer. And then the beam is received by a camera through a polarizer. Okay, so you get a speckle at the end. Am I good? Okay. From a signal processing point of view, you have 3 bottlenecks in this particular experiment. You have intensity-only measurements, and this is the point of this experiment. You don't have phase reference, so you have missing phases, and this can be something which has to be handled. Then, which can be difficult in this particular experiment, is the DMD, which only offers some binary positions. And okay, depending on the way you can handle that, you want to solve the problem, you want to consider the problem, it could be a problem inside the problem. All right. And then you don't have any idea about the transmission matrix. That means that you don't know, you have no analytical expression or numerical expression, whatever, about what happens between here the DMD and here the camera. So here your white paint layer is totally unknown and totally unwritable. So let's begin by this transmission matrix. Okay. I simplified the things. I told me, okay, this experiment is very much more too complicated, so I want something simpler. So here, this is what I receive. I have intensity-only measurements, so here, this is the moduli. And inside, I have a linear model because I want to be linear. So here, this is a transmission matrix I don't know. I want to infer, I want to estimate. And here, this is a binary vector, standing for the DMD, the DMD entries. Okay? So if I have P calibration signals, that means that for different P configurations of the DMD, I will get P different speakers, images. And I hope my transmission matrix isn't changed. Okay, so this is the same. So then, what I can do is conjugate, is a conjugate transposition. I can do that because I have my intensity only here measurement, so I can simply do that. I transpose my speakers matrix here. So this is the lines, actually. Each speckle is a line. The role of the transmission matrix is replaced by the DMD configurations. And here you have the transmission matrix I want to estimate. And this is nice, actually, because when I do that, I come back to an inverse problem. And this is treatable, actually, by any smart phase retrieval algorithm. Smart. Okay? So the idea here is that I can estimate every line of each line of my transmission matrix, one after the other, by considering here each rows, actually, of mine speaker matrix. Okay. Okay. I'm a Bayesian girl, so I want to do that from a Bayesian perspective. And this is much more difficult because when you have the moduli, you have to find a way to circumvent the nonlinearity of this kind of measurements. So a way to do that is to introduce hidden variables to take into account the missing phases of your measurements. So here you have your speakers, okay? Here you have a diagonal matrix in which each element here stands for the phases which we didn't observe on each pixel of the speaker. Okay? And I say, okay, I didn't know anything about these phases, but I know that this linear model, this is the assumption I make. Here, the matrix of the DMD configurations, and here, the line of the transmission matrix I want to estimate. And because it's not perfect, we have some noise. I assume that my noise is Gaussian, so that at the end, I get this particular distribution, conditional distribution of my observation given all my variables of interest. So this is Gaussian, and this is so the expectation of my Gaussian is this matrix multiplication is given by this matrix multiplication, and the variance is the one of the noise I assume to have. So this is my observation model. Then I need some prior models. Okay, that's easy for the phase noise because I don't know anything about the phase. I didn't observe them. So what I can just say is that, okay, they are in an interval comprised between 0 and 2 pi. What I can say is, what I can assume actually is that these phases are uniformly distributed into this interval, and this is what I put in my prior model for the phases. Then, for the transmission matrix elements, I expect them to be Gaussian. It would be good, actually. That they will be Gaussian, and this is what I assume here in this particular prior model. Okay. Okay, I have an observation model. I have prior models. Then I need an estimator. I choose one, for example, the maximum a posteriori estimator, which I wrote like that. So each element in my transmission matrix will be estimated according to the maximum of the posterior distribution. So given the observation I have. The observation I have, namely the line, to answer your question, the line here, this particular line, okay? And I will be interested in these particular elements of the matrix, of the transmission matrix. Sorry. The difficulty in that particular problem is that my posterior distribution has a complicated expression when I see that, okay, I didn't know anything about the phase, I don't want to estimate them, I want to marginalize over them. That means that I don't care. I just want to see if I sum over all possible realization of the phases, what I get, okay? And here I integrate also over all elements which are not the one I am interested in, okay? So this particular distribution, posterior distribution, will be handled by a mean field approximation. And I will say, okay, I need an approximation that factorizes like that. Okay, so I made a difference between the phase variable and the TM entries, but okay, you see that everything is assumed to be independent a posteriori and everything beautiful, okay? Okay, I won't enter into the analytical expression of the posterior distribution, but just to give you the most important message is that at each iteration you will update all factors of the approximation. So all elements in the transmission matrix, and we find at the end of the day that it follows. So these entries follows a posteriori a Gaussian distribution and of parameter mzn and sigma zn, which will be updated in an iterative way and taking into account the posterior distribution of the phase, where we have a von Mises distribution. So this is the computation will give you these results of those parameters. So you just have to iterate. Don't forget that you have to do that for every n here. So n for here for this particular part, and here for every phases in your problem. I didn't tell that at the beginning in the theoretical part, but indeed, when you have to deal with continuous variables, you have to deal with parameterized distribution, and what you have to update is are the parameters of the distribution. You can't deal with a continuous distribution, of course. Okay. So coming back to our problem, we look at the maximum a posteriori solution. So after convergence of the algorithm, you just have to compute this particular integration. And here, this is very simple in the case of mean field approximation, because you get the particular factor you are interested in. Okay, so Q of the I. And then we get, in this particular case, we are Gaussian. So you see that at the end you have, as an estimation of the matrix TM entries, you have the expectation, the expectation of the Gaussian a posteriori. Okay. So before I deal with the experiments, I did some preliminary synthetic experiments, and I think this could be interesting for you to see that. So here you have four different algorithms which are compared. In blue, this is Pierre Gamp, which relies on better approximation, and you see that it outperforms the other, which are mine. In red, so relying on the mean field approximation. And the two one here in black are deterministic algorithms. So here you have this cut, which was proposed by Irene Walsperger, which is a quite beautiful algorithm actually. And in a dash curve here, this is a older algorithm proposed by Gershberg and Saxton. Sorry. You have here the correlation. Sorry, I should have begun by that. Here you have the correlation between because I'm dealing with synthetic experiment. I know everything. Okay, so here this is a correlation between what I estimate. So here and the truth, how I construct my data. And this is what I'm measuring here, so the correlation between both, okay? And this is as a function of the number of measurements. So you have here the number of observations, actually, which is increasing, okay? Here you have the noiseless case. So at the beginning you don't have any observations, so you didn't manage to reconstruct anything, okay? And at the end, this is okay, better. So you have here the noiseless case, and here much more an increase in noise. I don't remember the variance of my noise. I'm sorry, but okay, you can find it in some papers. Okay, and what is interesting here, okay, is that Pierre Gamp, so based on the better approximation, outperformed the others in the noiseless case. But when you have some noise, you have a gap which is increasing between the mean field approximation and the beta approximation. And actually, this is just remember that this is a difficult case for the beta algorithm, beta approximation, because you have some loops here in the model. You have the observation here, so this is a variable, and here you have something that is a mess, actually, that combines everything, every entries in D, and to get to do something very bad with them, and to get to construct the observation. So you have many loops in your factor graph, and for the beta approximation is a difficult case. And when you add some noise, you get something which is much more difficult for the algorithm. Okay. So then I get to the experiments. In that case, I don't have any knowledge about the truth. So I considered the correlation, the reconstruction of the speakers. So in that case, I use my transmission matrix to construct the speckle I should get if I'm good in my estimation, and then compared with the speckles I really observed. Okay, so with the kind of for a given DMD configuration. So this is a kind of prediction correlation, kind of that. And so this is here MSE, so minimum square error between these both quantities, and here correlation. So we see that, okay, this is normal, that we have for one a decrease, normal, this is quite good, that the MSE decreases when alpha, this is the number of calibration signals, okay, that's increasing here. And so you have a decrease of the MSE when you get more calibration signals. And on the contrary, the correlation here will increase when the number of calibration signals increase. Okay. What is interesting here to see is that, okay, both fit very well, so it's quite good actually. And what is interesting is that you have a kind of plateau for a given number of calibration signals. So it increases, but very slowly at the end. Okay, then we try to check if the measured entries of the transmission matrix had some probabilistic characteristic. was indicated by the random matrix theory. And so we compute the singular values of the transmission matrix for different subsampling of the matrix. And here, for gamma equal to 1, you have the same number of rows and columns. And here you have 2 times the number of lines, 3, etc., etc. So you see that you have a quite good fit with the Marchenko-Pastur law, and just at the end, the gap is going increase between both the theoretical part and the singular value that we get, because we have a more correlated lines in the transmission matrix. But okay, it's quite okay. It's quite good. We are happy with that. Okay, once we have the transmission matrix, we would like to play with it. Sorry. And for example, we can do some focalization. So you already see, you already saw this scheme in a previous presentation. So it's a very, very beautiful scheme coming from Velkup and Mosk, this paper here. So the idea here is that I want some configuration of my speckle, so the observation Y, and I want to deduce the configuration of the DMD that that I need to get this particular speckle, okay, which is not much more speckle actually. So because it's complicated, I need to simplify the stuff. Here, this is the speckle I want. So it's not a speckle actually. The figure is not good. Try to imagine some kind of light and something blue around. Okay. And so this is the observation I want. Here, this is the matrix, the transmission matrix I've learned. And here, the DMD configuration I want to infer from the observation I want. So again, this is a phase retrieval problem. And from an observation, from a Bayesian point of view, you will resort to this kind of trick. So you introduce a hidden variable. You have the same observation as before. So I want to go longer on this particular part. The difference will be on a priori models. So you didn't know anything. You don't know anything about your phase. So it doesn't change. It didn't change. So you just have to. You can do. The only thing you can do is to say, okay, I assume my phase to be uniformly distributed over this particular interval. The thing will be about DMD elements. These elements are binary, so 0 or 1, and this is a point where Bayesian framework can be very good, because here you have a distribution which is perfect to deal with this kind of elements, which is the Bernoulli model, which depends on this parameter here, which is the probability of having z equal to 1. And this is where other phase retrieval, a deterministic phase retrieval algorithm can fail. Okay, then I need a Bayes estimator. I assume I have the same one with the same problem and with the same mean field approximation. And my algorithm will iterate between all these factors, so update all these factors one after the other. What's the difference is here, a posteriori, we get a distribution over the entries of the DMD, which are Bernoulli also, and the parameters of the Bernoulli law are updated according to every other entries of the DMD, and also the phase, which are assumed, which are computed at the end as a von Mises law, depending on these two parameters. Okay. So after convergence, you don't have Gaussian anymore, so you have something which is much more simpler, actually. You just have to make a simple thresholding operation by just putting to 1 the entries of the DMD for which we have the posterior distribution greater than 0.5 and 0 otherwise. Okay. So these are the results we get. Here again, as a function of the number of calibration signals. And here you have the enhancement factor. So, enhancement factor here. We compared 2 algorithms. So in red, this is mine. This is the Binfield approximation, and in blue here, this is a simple procedure, a phase conjugation procedure, in which you just keep the entrance, you just threshold, the real part of the phase conjugation. So you see something which follows actually the correlation curve we get when we tried to estimate the transmission matrix, and we see that with alpha equal to 3, that means that we have 3 more calibration signals than the size of the DMD. You will have some kind of plateau or an increase which is slower. And what is also interesting to see is that the phase conjugation works actually very well. Okay, so, and for multiple points, this is in French. You have here the enhancement factors as number of the number of targets, and also you see here the theoretical variation. So this is some observation you get in the literature, the variation in 1/t. So, you see that this corroborates. This is what we should expect in this kind of configuration. Okay. So I give you some references if you want to have more insights about this kind of use of variational approximation for optics with complex media. So this is a paper I wrote, and here, just after, Bushra Rajai works on a better approximation for calibration and imaging. And after that, you have this paper written by Christopher Messler, who wrote work also on a better approximation, and with a specific algorithm improvement. So this is a very good paper I can mention. Okay, so now I will speak about another application. Maybe it's more recent, or it's more recent for me, and it's a little bit more far from your works. I don't know. We'll see. Okay, so this is a problem of direction of arrival estimation in underwater acoustics. So the problem is that you have an antenna of a given number of sensors, which is, for example, an antenna put on a submarine, for example, and you don't send anything. You just want to hear, and you want to make as noise as possible, actually, and you want to hear the environment and to detect some sources which are coming from some directionals of arrival. So you don't want to make some mistakes, because after that you can maybe took some wrong actions. Okay, so when you have a propagation in a homogeneous medium, everything is okay. In a case of plane wave, you have your antenna here, and you get your plane wave, and you can say, okay, the source, the noise comes from this direction here. When you deal with this kind of ocean, you received an acoustic field on your antenna. So here on the particular sensor, which is the sum of different plane waves coming from different directions here, and with contribution Zi. Okay, and you had some noise. So from a dictionary perspective, you don't know exactly how many sources you have. Okay, so you have to search your sources in a big dictionary. Each column here corresponds to one particular direction of arrival, and each column of your dictionary will be weighted by a source contribution. Okay. Yes. Okay. This is when everything is okay, when your ocean is stable, but things are not so easy. And in real life, your wave will be confronted to different parts with different speed of sounds. So sometimes your sounds will be accelerated, and sometimes it will be decelerated. So at the end, on your antenna, you will get something which can be misleading, actually. So you can say, okay, according to a stable medium, a stable ocean, I will estimate that the direction of my noise is this way, but in fact it is this way. So it could be very difficult, actually, to deal with that. And so you have three different regimes of fluctuation. So this is a definition of Flatté. This is my PhD student, so he do this kind of this figure, and I thank him, actually. So three regimes of fluctuations. The first one will be is called the unsaturated regime. So you have a path here, you have a ray, and the ray goes through different inhomogeneities, but it doesn't create some diffraction of the path. And at the end, okay, it's difficult because you have a sort of deformation of the path, but it could be handled. When things are getting worse, you can have some diffraction of the path, and you have the creation of micropaths. But in this particular case, which is called the partially saturated regime, you get something which keeps a certain coherence. So each micropath is assumed to go through the same inhomogeneities. And when things are really, really getting worse, you get something like that. So you have a diffraction of the ray, and each micropath here will go through different inhomogeneities. So at the end, you get something which is very, very difficult to handle. So how does it impact the acoustic field? Okay. In the case of if you have no perturbation in the medium, you have something like that. Okay, this is the illustration of the received phase on a particular sensor. So here you have you will get something which has a bigger energy in one particular direction. So okay, you say my source is in this direction. Okay. If you have some inhomogeneities, and in particular if you are in the partially saturated regime, you will have something like that. So you have the principal direction of arrival, the true direction of arrival, but which presents some noise all around, so which can be which has to be taken into account. And in case of phase retrieval, you don't know anything about the phase. So that means that this is, for example, the case in the saturated regime. The phase is totally lost, or actually you have a so big noise that it's very, very, very difficult to go to the true one. Okay, so this is where we were actually in the 5 minutes ago, and this is now what we are going to to consider, so the phase noisy case. So again, this is the model you know per heart now. So this is the observation. So here, this is the acoustic pressure I have. Here, I will get the phase noise on each particular sensor of my antenna. And the phase noise here actually brings the random phenomena. In the following application, the random phenomenon was here in the transmission matrix. In that case, this is here that you can find some random phenomena to be taken into account. So here the dictionary of steering vector, so of direction of arrival, and here the contribution of the source. You get your observation model, then you need your prior models. So for the phase noise, for this time we have some information. We know that, okay, this is not totally lost. We don't have any information at all over the phase. We know that we will be centered over something which can be deduced, which can be inferred. And all around, you have a little distribution, a Gaussian distribution. And what is important here to mention is that in that particular correlation matrix, you can put every physical information you have on the medium. For example, in underwater acoustics, you know you can compute, you can have some information about the coherence radius of your measurements, and this can be taken into account in this particular parameter, probabilistic parameter. For the DOA model, so the direction of arrival model, we will take something which is a little bit more complex than before. We will take a Bernoulli Gaussian model. This is well-known. This is a well-known model in Bayesian sparsity, in which actually you say, okay, my sources will be the product of one Gaussian variable and a binary variable, so Bernoulli variable and a Gaussian one. And if the Bernoulli parameter is getting to 0, then we don't have any contribution of the source. Okay, so this model is well known, as I said, in Bayesian sparsity, and has been motivated by the identification of with the standard L0 sparse problem. If you are familiar with this kind of representation. Okay. So I have my observation model, my prior model. So I need now a based estimator. And to this time, I will take the MMSE estimation. So this kind of estimator, when I want to minimize the expectation according to the quadratic error. As before, I will need an expression of my posterior distribution, and I will resort to a mean-field approximation. In that case, however, I will not completely distribute, I will not completely break the links between all variables. I will say, okay, I have a factorization on independence between the phase and the contributions of my sources, but my sources, which are described as a product of two different variables, I will keep these two variables together. Okay. And actually, I do that because less links you break, better is it. Actually, in the midfield approximation, you can do whatever you want. Actually, you don't need to break every links in your posterior distribution, but this is easier to handle in the computation. Actually, this is just because it's easier to compute that we do this kind of factorization. If you can keep some of them, then keep them. So the VBM algorithm we have is something like that. You have you have a distribution, a posterior distribution over the contribution of the sources, which are totally similar as the one we get on prior. And this is the same also for the phase. You update every parameters, all parameters of your distribution iteratively. Okay, so after convergence of the algorithm, you get something here which can take into account, so the I here, so the contribution of the sources will be the product of the expectation of the Gaussian and the parameter of the Bernoulli parameter here. Okay, so this is 0, maybe, or equal to the expectation of the Gaussian. Okay, this is much more difficult to get some real data in underwater acoustics, but I get I did some synthetic experiments. Here I get 100 sensor antenna, and I have a dictionary of 15 direction of arrivals and k incident waves. And I consider a phase noise which obeys a Markov chain. This is not. This is actually well. This has a nice physical interpretation because you assume like that the phase noise that affects one particular sensor is not so far from the phase noise that affects the neighborhood actually. Okay, but for the beginning, I will say, okay, I have a big noise for my first phase noise, so I don't know anything about the first one, but I know that then they could be linked or not so far one from the other. Okay. I consider again the correlation, the normalized correlation between the true direction of arrival, so the true contribution of the sources, as this time as a function of the additive noise. Okay, and here this is for 4 different algorithms. So in red, this is the mean field algorithm. In blue, the beta approximation, and in the continuous line here, you have the phase retrieval algorithm. So the one I used for to estimate the transmission matrix just in the optics application. So you don't consider any noise, any information on the phase noise. Sorry. And here in dashed line, this is a beamforming approach, a classical beamforming approach. So here, this is for 1 sources, 2 sources, and 5 sources. And you see that, okay, again, the mean field approximation address the problem quite well with a comparison to the other one. And more interesting here is that, as you see, when you had some more sources, this is counterintuitive, but this is more easy for the algorithm to find the contribution of the sources, and this is quite. This is actually typical for the phase retrieval problem, because if you consider 1 sources, for example, in this particular case, 1 sources, to choose the right columns of your dictionary will be very difficult because they have the same moduli. So you will fail. Well, it will be difficult actually to find the right direction of arrival, and if you don't have any other information, for example, here in that case, you just fail. Okay. So when you had some sources, you get a better results. And here, this is when you increase the noise, so the transmission variance between in your Markov chain. Okay, I'm almost done actually. So take-home message. I hope I have convinced you that the Bayesian framework could be helpful for you. Two things to get. So you need a probabilistic modelization, but actually for you it's a good thing. Because in this probabilistic modelization, you can put some physics on your problems. You just have to consider the right one, actually. And this is good because you can quantify the information and the uncertainties you have on this particular model also. What is interesting also is the variational approximations, which are a good alternative to the Monte Carlo methods, much less time-consuming and much more elegant, in my opinion. And these are based on approximation of posterior distribution. Okay, and you get some efficient procedure to compute them. Thank you very much for your attention.